welcome. You can see today is day 22. What we're going to do is we're going to start our actual content once again, finally, after about 2 weeks. So, what we are going to do is that you see the goal of today is to figure out what a speed of a wave is dependent on entirely. And if you notice our agenda, what I'm going to do is I'm going to take care of some bookkeeping first. We're going to talk about our Zoom results, what exactly happened there, what are we going to do. I want to review a little bit with you, talking about what exactly we were talking about before our break, kind of go over that because it's been a while. And then finally, we are going to do an activity together, and I'm going to try and get you to understand a big conclusion as to what is the speed of a wave dependent on. Next time, I'm going to hope that you are able to complete a lab through the same application, something that I'm currently writing right now, but that's kind of where we're going, and that's the idea. Now, homework-wise, if you notice our homework, what I want you to do is that we were working on that speed of the waves lab and then the report, and I'm hoping for it by the end of the week. So, a lot of you have already turned this in, and I understand that, and that's fantastic. Some of you have not, and I know that there's been a lot of questions as to what you can do and what we are able to do through this distance and through this electronic means. So what I'm going to do is this first. Number one is that let's go first into our Canvas page, and this is our Canvas page just as it stands right now. If you notice, if you go into the assignments, now at this time, that if we go into assignments and then, come on, whenever we click on that actual lab, the speed of the waves lab, you notice the new due date. What I have is that I have right up here, now we are able to do online submissions. So if you still have that lab with you, I want you to submit it electronically through Canvas in this manner. And you might think to yourself, well, Mr. Tate, what in the world? I have my lab, which is a piece of paper, and then I have my typed out essay that's electronic. How do I do that? Well, hold on. If we go back, as I said, and as I was hoping to get you all to understand, we were going and we were trying. Oh, where'd I go? We were going and we were trying specifically to figure out a application in a way in which you can figure out how to exactly turn in assignments. There we go. How you were able to turn in assignments electronically. So the idea is that I went and I found us an app, and it is Google Photo Scan. It is available on your phones. So what you would do is you would go and you would take a photo of it with Google Photo Scan and then submit it in that way. That way we can have both the electronic and the paper copy submitted in the same spot. That's the idea, and that's kind of where I'm going. So, I'm hoping for that by the end of the week, but I am going to tell you to pause sometime during this video and say if you have not completed that, go and complete that now. That's our main idea. So there's check one. Number two, let's talk about the Zoom. So our Zoom results, most of you went and you voted saying that every Tuesday, Thursday in the morning would work out best for you. What we are going to do is that if you take a look at the schedule, I know a lot of teachers are doing synchronous learning, meaning that my normal time that I was hoping at 10 to 11 a.m. is not going to work out. I know some teachers are really expecting you to be there during that class time nowadays. So what I am going to do is that we have a 45-minute block called conference time on this new schedule, and I am going to be at Zoom, and it's a reoccurring meeting every Tuesday and Thursday from 11:15 until noon. Now, the idea here is that you can use that meeting ID posted down at the bottom there, and you would be able to go through and specifically just join the meeting. It does not have to be a required attendance. You only come if you have questions, you want to work on something with me, anything of the sort there. It is not a requirement that you stay for the entire time. You can hop in at 11:30, ask me one question, be out at 11:35. Fantastic. I'm going to record every single one again and post them up to the YouTube page, much like what I've been doing, and that way everyone can be kind of caught up at the same time. So that's where we're going, and if you notice, that's our idea. Now, let's get back to content of before spring break, we were trying to answer one really, really big question, and it is right here. What happens whenever two waves come into contact with each other? Specifically, you had started that speed of the wave slab, and we were going, and I was having you create amplitudes and send out different amounts of energy, trying to see what happens to that wave. And eventually, you started out that some of the waves start colliding whenever it comes back on like the crest of that wave. Then it really makes a difference as to what's going to happen. So we went and we talked a little bit about the superposition principle, talking of how whenever two waves collide, you go and you add together the amplitudes. With the superposition principle, you can have one of two ways. It is either constructive or destructive interference. Constructive is whenever the amplitude is enlarged because of two resulting waves, and destructive is whenever the amplitude is decreased because of two resulting waves. So if I have interference, interference always just depends on the phase. So specifically, if I want constructive interference, you notice that whenever well, let's wait for constructive, but whenever the crest and another crest meet, just right here, you see if I can't do this, but if I want to go and I want to say whenever the crests meet, you notice right here, this creates constructive interference. And whenever the crest and the trough meet at the same exact spot here, so you'll see this is just our equilibrium. Whenever our crest and our trough meet here, this is going to be destructive interference. So it depends on phase, and phase just means what part of the wave hits at each specific time. Now, going forward again, I have bunches and bunches and bunches of examples of what happens whenever you have two phases intersect and meet each other. That if it's reflected on a closed surface, such as like a wall and a sound wave, then it's flipped along the x-axis, and you can see that the wave then goes kind of underneath itself, even like right here whenever it's going in, it's traveling. So it's traveling first here up at the top, and then whenever it's reflected, it's going and is reflected on the other side of the x-axis. Or for the y-axis, it's for an open surface, such as, like a ring at the end of a stand or something of the sort. So whenever you have a y-axis reflection, it's always because of an open surface. So this is our idea, and this is where we started out. And you get lots and lots of really, really cool examples whenever you get this type of interference. Now, this thing at the bottom right now is called a standing wave, and you're going to get there. But we have to first figure out what the speed of a wave is dependent on. I know some of you with your labs, you're not very confident with that, and that's okay. As I said, the entire purpose of that is for it to be a start. It's our hypothesis. What do you think happens to the speed of a wave as we add more energy? So, what I am going to do is that I am going to show you an online simulation, and we are going to do it together. But I want you to be very, very clear. I do not want to run this simulation with you if you have not finished your lab, because then or rather the results of this simulation are going to skew those results. And if we skew those results, then immediately your lab is no longer beneficial in the manner in which I wanted. So now is the point. If you have not finished your speed of the waves lab and your conclusion, pause the video right now, go and complete that first, then come back. All right? All right, let's do it together. So what we are going to do is that as soon as, oh, no, I don't want to keep those. Let's go into this simulation. So this simulation, what you can see, and let's make myself tiny here, is that I have just a string, and I can go and I can send a specific amplitude. And if I change my amplitude, I am going to set an amplitude and then set it to normal. You notice that there's no end here, high tension, zero damping, meaning that there's no friction also, and I am going to oscillate this string. So if I go and I create a wave, fantastic. Now, what I am going to do with you is that I am going to try and figure out the speed of this wave. Now, let's take a look and see a little, or rather a couple of things in which we need. The first thing is that if you notice, my amplitude right now is 0.50 centimeters, and my frequency for easy math is 1.00 hertz. So what I am going to do is that first off, over here, I am going to start writing all of our variables. So my amplitude, no, amplitude, Down here over the side, I am going to start out with 0.50 centimeters, 50 centimeters, and a frequency of 1.00 hertz. If you notice, I am going to keep the same frequency all the way down, but I am going to be changing the amplitude and we are going to be measuring the wavelength on this together. So here's the main idea. Whenever I am going to do this, yeah, I want to keep those for a second. I want you first to think, on this simulation, what is my wavelength going to be? And you start thinking to yourself, well, a wavelength should be parts of the equilibrium in which it is equal from each other. And what I mean by that is that first, let's do a couple of things. Number one, I'm going to get a ruler out for this, and we are going to try and measure this wavelength. Now, right now it's moving way, way, way too fast. So what I'm going to do is I'm going to set it into slow motion. Whenever I bring it up to the equilibrium, about right there, I'm going to wait until that first part right here hits that 0 mark. So give it a second, give it a second, there. Okay, and I want you to think, what is going to be the wavelength now? Now think, a wavelength includes one crest and one trough. It has to be back to the original section of the wave. So if you think my wavelength here is all the way down to the 3 centimeters is my crest or is my trough, and then up to the I'd say 6.1 centimeters is going to be my wavelength. Okay, so I'm going to go back over here and I am going to write down that 6.1 centimeters as my wavelength. So then 6.1 centimeters. Now, if I want to find the velocity of this wave, remember that the velocity of a wave is always going to be the wavelength times the frequency, or my velocity is going to be equal to my wavelength divided by my period, which is capital T. Now, I'm going to use this one up here because this seems a lot easier for me, and I am going to say that my velocity is 6.1 centimeters per second because 1 hertz is a 1 over second. So 6.1 centimeters per second is the speed of the wave on that simulation currently. Let's now change my amplitude and let's just make it 1.00 centimeters. And again, I'm going to measure that wavelength. So let's go back. No, no, no. Ruining the experiment. All right, amplitude 1.00 centimeters. So you are right. I have just doubled now the energy in which this wave has. Amplitude correlates to the amount of energy. Think like volume on an amp or something of the sort. If you turn up the amplitude, you're turning up the volume, the energy. And I'm going to reset, move my ruler, turn it back, and you will notice my wave is now a much, much higher and a much more aggressive wave function. But what I am going to do is I'm going to do the same thing. I'm going to set it to slow motion. I'm going to wait until I can get the same exact thing, pause, and now I'm going to bring my ruler down and again try to measure the wave function from the start through one crest, through one trough, and then back to the original. And if you notice, it again is 6.1 centimeters for my wavelength. So just let's keep it as is for trial 2 as 1.00 centimeters, and let's crank it all the way up to the 1.25 centimeters. I want you to first make a hypothesis. What do you think the wavelength is going to be whenever I reset it? So let's try it. This is the highest possible that it can go, and if you notice, whenever I go and I let it run for a bit, here I'll just let it run, keep on going. Maybe the amount of time is influential in the wavelength of this wave until eventually I'm going to set it to slow motion. Wait, get it at a good one. Oh, that wasn't too great. Maybe a little bit more. Hey, there we go. And what do you notice for the wavelength? Again, one trough and one crest, and it ends back at 6.1 centimeters. So I want you to think right now of what we're doing and what we're figuring out is that it doesn't matter. Wait, what was my amplitude? 1.25. Okay. But it does not matter what exactly I have. If I go, oh, and I try and figure out what exactly my amplitude is going to be, 1.00 centimeters or 1.25 centimeters, every single time my wavelength was 6.1 centimeters. It did not matter how much energy I put through on this wave. The amplitude is the energy. If I change the amplitude, I'm changing the amount of energy, but if you notice, my frequency stayed the same. So every single time, it's going to be the wavelength times the frequency, and every single time, I am going to get 6.1 centimeters per second. The idea here is that the velocity of this wave, even though I changed my amplitude, it did not change. Some of you on your labs probably noticed that it went up and then down and then it was left and right, and it really didn't make any sense because your data did not follow a conclusion. The reasoning for that is because you had a lot of error in your timing. The velocity of a wave is very dependent on the medium alone. The velocity of a wave does not change unless you change the material in which the wave is traveling through. So what I want you to think about right now is that I have this video of a firework, and I am going to first just let this video run, and I want you to notice the sound difference, or specifically, when does the sound occur? So what did you notice? Let's once again just go back, see if I can't do it again. I want you to notice the timing difference between whenever the light hits and then whenever you hear the sound. Do you notice how the sound comes after the light? It's because the speed of light is faster in air than it is sound. Both of those have a specific velocity, but it's dependent on the air alone. You have to change the air in order to change the velocity. So, let's now figure out what happens when you change the air. And this is always one of my favorite demos, but I'll tell you a really, really good story about this afterwards. So, by itself, what Mythbusters, and specifically Adam Savage, is going and showing here is that he changed the air of the sound wave travels the same. You can still understand him because the frequencies in which you know to represent words still works. You can still understand him, but now he sounds differently because he changed the air in which that sound wave was traveling through either helium or sulfur hexafluoride. I love this demonstration, but the problem is that inhaling sulfur hexafluoride is really, really dangerous. My AP Chem teacher in high school used to do it, and he always used to tell us because helium is less dense than air. So if you go and sometimes you get lightheaded whenever you're inhaling helium, it's because you don't have enough oxygen. Remember, helium's a noble gas and is unreactive. So you can inhale it, it's fine, but you run out of oxygen. So imagine if you don't have enough oxygen, you go and you pass out. With helium, fine, it releases itself. If you're laying down, it's less dense than air. Sulfur hexafluoride is the opposite, though. It's more dense than air. So if you inhale sulfur hexafluoride and you pass out, there's no way for that sulfur hexafluoride to get out of your lungs without some assistance. It's a really, really dangerous demo, but it's really, really cool. So this is the big idea. And this is what you are going to be working with next time, is that specifically the speed of a wave depends on the medium. What I mean by that, we can add as much energy to a wave as what we want. It does not matter. We can change the amplitude again to whatever in the world I want. The higher the amplitude, the more energy I have in that wave. But if I change the amplitude, then you would assume that the speed of the wave changes as a result, and it doesn't. Waves depend on the medium. It's like, again, Think of it. If you go and you tap on like a wall or something of the sort, you can hear how that wave travels through that wall. Think of like tapping on wood as opposed to tapping on metal. There's a different sound associated with each specifically because you're changing the speed of that wave. So think of it this way: the speed of a wave does not depend on the energy. You can add as much energy as you want, and that speed of a wave will not change. That's what your lab is supposed to figure out. Now, I do not want you to change your lab. As I said, it's a hypothesis. Hopefully, if you've already written it, turn it in. If you've already turned it in, fantastic. There is no changing it now because now we get to learn and we get to move on with this idea. So here's the idea. Next time, what you are going to do is that you are going to perform that standing waves lab, specifically using that exact same application with the window off to the side that I showed you today. That I'm going to be posting that for class on Wednesday. But this Tuesday coming up, we are going to have our very first Zoom session from 11:15 to noon. So if I go all the way back, remember, this is the Zoom session ID, and it's not mandatory. It's just to come in and say hi. So everyone, I hope you're doing fantastic. We really do miss you all, and be safe.